Hi, welcome to this video on kinematics. Focus 2, motion graphs. Let's begin. Now for motion graph, the central idea is gradient and area. Now when we calculate the gradient of a straight line, let's say we are actually taking the y-axis value divided by the x-axis value. And in doing so, we are actually finding the amount of y for every 1x. Okay, I will reiterate this point later when we go to the graphs proper. Now for area, okay, the math involved here is not within our scope, so I'll just inform you that when you find the area between the graph and the horizontal axis, we are actually finding the quantity of y multiply x. Okay. Also, before we start going into the graphs, we will try to recall here what is meant by vectors, because later we will be dealing with vectors such as displacement or velocity. Vectors are physical quantities with magnitude, which is the value, as well as direction. So it is important to assign or define a particular direction which we will take as positive, and whereby then the opposite direction will then be taken as negative. So usually when no information is given in the question, we will then, by convention, which means by habit, by usual practice, we will take the right direction to be positive in horizontal movement, or for vertical, we will then take upward as positive. Now let's go into the displacement time graph now. Point number 1, you can read it. Now point number 2, this is the most important here. The gradient of the line that joins 2 points on the graph will give us the average velocity of that object between that 2 points. It may seem like a long statement, potentially confusing. It's summed up here actually. So remember, like a few minutes ago, I mentioned that the gradient gave us the y-axis value divided by the x-axis value. So for displacement time graph, the gradient tells us how much displacement change there is for every 1 unit time. And in my example, our 1 unit time will be seconds. So if you can recall the formula from the previous video, displacement divided by time is therefore velocity. Okay, so just to sum it up, gradient give us y-axis value divided by x-axis value, displacement divided by time. Now let's look at the displacement time graphs of some common motion. Number 1, at rest. At rest means stationary, so the object remains in its position. That is why if you look at the graph, which I have deliberately put in some numbers so that we can visualize or imagine more easily. Okay, throughout the 3 seconds, for example, the position did not change, so it's at displacement 4. That is why we observe a horizontal line of 0 gradient. Okay, now recall, gradient gives me velocity, 0 gradient, 0 slope. Slope is another word for gradient, therefore correspond to 0 velocity. That is why at rest. Okay, like in this picture. Now when it comes to displacement, it's useful that you try to imagine that a moving object or the object itself is on a gigantic ruler on the floor and is moving along this ruler to and fro. 2, constant velocity. The object is moving with constant velocity or constant speed, if you like. That means that in every second, look at this, every subsequent next second, it covers the same distance or experience a same equal change in displacement. In this case, 2, 4, 6. And due to this, you therefore get a straight line of a certain positive value gradient. Okay, so constant gradient, therefore constant velocity. How will it look like if it moves like this? Okay, so note that every second it covers the same distance, and if I can take a picture of this moving object every second, you will notice that they are equally spaced out. So in a subsequent explanation, I'll go slightly faster, okay, to the point. So for increasing velocity is speeding up, so we call it acceleration. Every subsequent second, you see that the change in displacement gets larger and larger, meaning that it speeds up. In terms of the line, you will see a curve this way with increasing gradient, which is a result of larger and larger displacement for every subsequent second. Increasing gradient, increasing velocity. If you take a picture of the object every second, you will notice that the distance between subsequent ones get larger and larger. Or we can say that the displacement in every second gets larger. How will it look like if it moves like this? Okay, it gets faster and faster. Now, decelerating. Every subsequent second, the change in displacement gets less and less, meaning that it slows down. You will see a curve of decreasing gradient, therefore decreasing gradient, decreasing velocity. It looks like this when it moves. Okay. Now let's look at one example. Displacement time graph. You can pause the video and read it. So number one, describe the motion of the car in 20 seconds. When you see a graph, always try to identify the distinct parts, which we have here: yellow, pink, and green. Increasing gradient, so increasing velocity or accelerating. Constant gradient, constant velocity or uniform velocity. Decreasing gradient, so decreasing velocity. Now what's the average velocity? Remember, we said that it is the gradient of the line that joins the 2 points. So I started at, for the whole journey, so start at 0 seconds, end at 20 seconds. Now the coordinates as shown, 27 and so on. So the gradient, if you do y1 minus y2 over x1 minus x2, or more specifically, more correctly in this case, it is displacement 1 minus displacement 2, time 1 minus time 2. We have this right here. Okay, so this is the answer. So I need you to see the relationship, the correlationship between gradient and the actual formula. The gradient, displacement 1 minus displacement 2, it actually gives us the change in displacement. And t1 minus t2, 20 minus 0, give us the time for the journey. All right. Okay, now it's your turn to try out one question. Okay, so you see, we look at how we do this question. We observe the shape of the graph. So notice here, constant gradient, decreasing gradient, zero gradient. So constant velocity, decreasing velocity, zero velocity. Answer is A. 2. Calculate the average velocity. So it's a gradient of the line that joins the 2 points, 0 to 4 seconds, 0 to 10. Now I've marked them out. 0 to 4, this green line. 0 to 10, this red line. So we're finding the gradient of the green line and red line respectively right here. 6. So the change in displacement for 0 to 4 is 6. The time taken is 4. For 0 to 10, the change in displacement, it starts from 0, position 0, all the way to 12, right here. Divide by 10 seconds. B. Okay, let's move on to velocity time graph. For velocity time graph, there are 2 important points. The first one, similar to the earlier one, that is the gradient, give us the vertical axis value divided by the horizontal axis value. So for velocity time graph, the gradient gives me velocity divided by time, which is acceleration. For velocity time graph, there's one more thing, that is the area. Okay, so right here, if you read, when the velocity is positive, later we will look at negative. So for now, when the velocity is positive, the displacement is given by the area under the graph. So remember earlier, we said area is y times x. So if you get an area, of a velocity time graph, you are taking velocity multiplied by time, which is the displacement. Okay, let's look at this first graph. Object is stationary. So since it's stationary, the velocity is 0 throughout. You will see a 0 gradient line of value 0, meaning on the time axis itself, like this. How about object moving with constant velocity? So this is the velocity time graph, remember. So right here in my illustration, the object is moving with constant velocity of 4. At every point in time, the velocity remains at 4. That's why you see a horizontal line of 0 gradient, value 4. Okay, so 0 gradient, 0 acceleration, remember. And 0 acceleration corresponds to constant velocity. It looks like this when it moves. Every second, it covers the same distance. Okay. Constant acceleration is speeding up. And the word constant here means that every subsequent second, the increase in velocity is fixed. In this case, 2. It gains 2 meters per second in every second. That is why the unit for acceleration is 2 meters per second squared. So if you look at the gradient, it's a constant positive gradient, so constant positive acceleration. It's speeding up, so you see the distance between the object in every subsequent second gets larger and larger. It looks like this when it moves, getting faster each time. Now, remember earlier we talked about the area being the distance traveled or the displacement. So this area, if you calculate this area, which is 3 times 4 is 12, that is the displacement. So we say that the object has moved forward by 12. This area corresponds to this displacement. Number 4, increasing acceleration. Now I have to explain this together with number 5, decreasing acceleration. Now take note that in both cases they are accelerating. So you notice that the velocity is going up. Just that because of the curve, we know that the velocity is increasing in a different manner or different trend. For number 4, the first graph you see here, the increase in velocity takes on larger and larger values. So increase by 2, increase by 4, increase by 8. That's what we mean by increasing acceleration. What you notice is the gradient, because of this increment, the gradient initially is shallow, is a gentle gradient, subsequently increasingly steep. So we notice you will see a graph of increasing gradient that corresponds to the increasing acceleration. Okay, how will it look like? It speeds up like that. Now, how about decreasing acceleration? Now, do not be deceived by the term decreasing. So that's a common problem by students. They see the term decreasing, they thought it is slowing down. No, it is speeding up. And the term decreasing means that the speeding up gets weaker and weaker, but still speeding up. So let's take a look. In the first second, increase velocity by 8, and then increase by 4, followed by increase by 2. It is increasing, must really see this point here. It is increasing, just that every second the increase gets less and less. That's what we mean by a decreasing acceleration. So you will see that we have a gradient of a graph of decreasing gradient that corresponds to the decreasing acceleration. It looks like this when it moves. Okay, still speeding up. In both cases, you see that the car speeds up. Now, the area gives the displacement. I want you to take note that these two areas, compare these two graphs. This is a larger area, that is why it covers a greater displacement. Smaller area, shorter displacement. Now let's go to deceleration, slowing down. So the velocity drop. Uniform, a fixed drop of velocity in every second. You will see constant negative gradient that correspond to constant negative acceleration. Negative acceleration is deceleration. So it slows down like that. Okay. So this area give the displacement. Again, I'll explain 7 and 8 together. So we have deceleration for both cases. You will notice that the graph goes downwards in general. And increasing deceleration means that for every subsequent second, you'll notice that the drop in velocity gets more and more. That's what we mean by increasing deceleration. You will see a graph of negative gradient, and not just that, increasingly negative gradient. Okay, so it goes like this. Slows down. So the next graph, graph 8, is just another kind of slowing down, is decreasing deceleration. So initially the drop is large, subsequently it gets smaller and smaller, the drop in velocity. Decreasingly negative gradient corresponds to a decreasingly deceleration. So it looks like this. Slow down as well. Now, again, the area. This area is larger, so you notice a larger displacement. Okay, time to look at one example. You can pause the video to read. So here we go. Describe the motion. So we have yellow, constant gradient, zero gradient, increasingly negative gradient. So constant acceleration, zero acceleration that corresponds to uniform velocity, and increasing deceleration. Part B, determine the acceleration. So remember, it's a gradient of the graph, or in this case, I'm actually using the acceleration formula. So take a look. V minus u over the time. Again, I need you to see that this is in fact a gradient formula. y1 minus y2 as a numerator, x1 minus x2 as a denominator. Part C. The cheetah covered a certain distance, ran this amount in the last 4 seconds, which I mark out as this green area, that is 97.5. Calculate the total displacement of the cheetah for the entire journey. So we need to find the total area, we need to find the yellow area and add it to the green. So the displacement will be area under graph from 0 to 8, which is a trapezium right here. Add to the 97.5, we got this amount. That is a total displacement. To get the average velocity, take this total displacement, divide by the total time. That gave us the average velocity. Now example 3 is slightly more complicated because it has negative velocity. So remember, the very first slide we talked about vectors. Positive being travel in a particular direction, we call it forward, and then negative is where it travel backwards. When nothing is said, we will take right side to be the positive. Remember? Okay, so just look at this graph in general. The part that I highlight yellow is positive velocity, so it's going forward. The one in green, negative velocity, is going backwards. So part A, describe the motion for this entire journey, in fact. So very quickly, constant positive gradient, constant acceleration, zero acceleration or uniform velocity, negative gradient, constant negative gradient, constant deceleration. Now the word constant and uniform, they are the same. When you have a graph with positive and negative velocity, you then have to be clear and be specific and mention moving forward. The green part, they are moving backwards, so you see opposite direction. So here is a bit tricky. For negative velocity, things are slightly different. I remind you, the negative means that it's going the opposite direction. Now if you think about the value from 25 seconds to 30 seconds, the value of the velocity, that is the speed actually, changes from 0 to 3. That means it's actually speeding up. It is speeding up in the opposite direction because of the negative sign. So uniform acceleration right here in the opposite direction. So now take a look. Between moving forward and moving backward, at time 25 the velocity is 0, so we say it's stationary. At that very moment we call it momentarily. So now we move on 30 to 40 seconds. Again, the value of the speed changes from 3 to 0, so it is slowing down, decelerate in the opposite direction. Calculate the acceleration of the fish. So this is quite easy for at this moment. At this point in time, it should be easy for you. 3 divided by 10, you get this acceleration. C, furthest distance traveled forward. Remember, forward, positive velocity. So we find this area. It's the area of trapezium right here, 52.5. So what we are saying is this fish from 0 to 25 seconds, it traveled forward to here. D, calculate the displacement of the fish from its original position at 40. So you need to now understand that this green area, okay, give us the displacement in the opposite direction. You calculate this green area is 22.5. So the fish traveled forward 52.5 as calculated previously, and then moving back 22.5. Right, and here I want to mention something. When the velocity is negative, then the displacement is given by area above the graph. That is this green area above this graph. Okay, your turn to try the next few questions. Question 3. The answer is acceleration start to decrease. So replace the word acceleration with gradient, because you know that gradient of a velocity time graph gives the acceleration. So which point the gradient start to decrease is point C, where initially it's steep and you see that it gets gentler, the slope of the line gets gentler as we go. Question 4. So we just have to do for the different time period, find the acceleration. 40 divided by 2, we got it. Now deceleration. Here, I just want to remind you, use this formula confidently. Determine the final and initial velocity. The final velocity being 0, the initial being 40. Because we're talking about the time period from 2 seconds to 6. I only care about this part. The final velocity is 0. That's how you get a negative value. Now, when the acceleration is a negative 10, the deceleration will just be the positive value 10, because the term deceleration already means slowing down. So we do not need a negative sign in this term that already means slowing down. The displacement given by this yellow area is a simple area of triangle. So 1, 2, 0, we got it. The last question. The diagram shows the velocity time graph for the motion of a body. So you see there's a positive velocity and negative velocity this time around. Okay, I'm going to provide a full analysis of the motion of this object. The yellow area traveled forward 11. The green area traveled back 2. Okay, so it went forward 0 to 4 seconds. It traveled forward 11. And remember that we said earlier, at this point when the velocity is 0, it changes direction. Okay, this green area, it traveled to like this. So I'm now trying to mimic the motion of this object starting from 0. It went forward 11. In order to change direction, you have to stop, and then it comes back. So conclusion, whenever an object is moving in a straight line and it changes direction, the point when it changes direction, the velocity must be 0. It's an indication of direction change. Okay, so we have the answer A.
Hi everyone, I hope this video lesson has helped you in re-establishing a solid foundation for this topic. In this way, we can then move on to higher challenges in the theoretical part of the subject. For practical training, we have a fully equipped physics lab to provide hands-on sessions for our students. To find out more, please reach out to us through this media. We will see you soon.